Estimating Single Population Parameters. This is from the Chapter 8 of the book Business Statistics, a Decision-Making Approach, 8th edition. Why you need to know. Wherever you find yourself working, you may need to know population values or parameters to help you make decisions. A bank manager needs to know the percentage of loan accounts that are past due. A human resource manager might wish to know the average hourly wage for skilled labor in the company's hiring area. And a manufacturing manager needs to know the average machine downtime in his plant. Or the programming manager at a major television network needs to know the percentage of people watching each of his shows so he can cancel the poor performers. In these cases, and many others like them, decision makers need to know a population parameter. However, gaining access to an entire population is extremely expensive and time consuming, and in many cases, infeasible. Therefore, an alternative approach is to select a sample from the population. The sample data are used to compute a desired statistic that forms an estimate of the corresponding population parameter. After completing this chapter, you should be able to distinguish between a point estimate and a confidence interval estimate, construct and interpret a confidence interval estimate for a single population mean using both the z and t distributions, determine the required sample size to estimate a single population mean within a specified margin of error, and perform and interpret a confidence interval estimate for a single population proportion. Now let's begin with point estimates. For example, every election year, political parties and news agencies conduct polls. These polls attempt to determine the percentage of voters who will favor a particular candidate or a particular issue. Suppose a poll indicates that 33% of the people in the voting age is in favor of Rodrigo Duterte as president. The pollsters have not contacted every person in the country, rather, they have sampled only a relatively few people to arrive at the 33% figure. In statistical terminology, the 33% is the point estimate of the true population percentage of people who favor Duterte as president. Simply speaking, a point estimate is a single statistic determined from a sample that is used to estimate the corresponding population parameter. Which point estimator the decision maker uses depends on the population characteristic the decision maker wishes to estimate. However, regardless of the population value being estimated, we always expect a sampling error which cannot be eliminated. Sampling error is the difference between a measure computed from a sample and the corresponding measure computed from the population. Now, to overcome the sampling error problem with point estimates, the most common procedure is to calculate an interval known as a confidence interval. A confidence interval is a percentage from the lower to the upper confidence limit where the true population parameter resides. It answers the question, how much uncertainty is associated with a point estimate of a population parameter? Let us have a run-through on the estimation process. From the population, we generally don't know what the population mean is. So, what we do is to get a sample from the population and compute for the sample mean. We can then estimate the population mean from the sample mean we've just computed with a certain level of confidence. The general formula for computing the confidence interval is as follows. The point estimate plus minus the critical value multiplied by the standard error. When the population standard deviation is known, we first need to specify the confidence level that is needed to determine the critical value. The confidence level could be at 99%, 95%, or any values less than 100%, depending on the confidence of the decision maker on the sample data. Once you decided on the confidence level, the next step is to determine the critical values. The table here shows the critical values for commonly used confidence level, and the standard error can be computed by dividing the population standard deviation by the square root of the sample size. This then gives us the formula as shown here. For computing the confidence interval estimate when the population standard deviation is known. Additional assumption when using this formula is that the population should be normally distributed, and if not, a large sample size should be used. Let us look at an example. Nagel Beverage Company. The Nagel Beverage Company has recently installed a new soft drink filling machine that allows the operator to adjust the mean fill quantity. However, no matter what the mean setting, the actual volume of the liquid in each soft drink can will vary. The machine has been carefully tested and is known to fill cans with an amount of liquid that has a standard deviation of 0.2 ounce. The filling machine has been adjusted to fill cans at an average of 12 ounces. After running the machine for several hours, a simple random sample of 100 cans is selected, and the amount or the volume of soda in each can is measured in the company's quality lab. The sample mean computed from 100 cans is 12.09 ounces. The sample of 100 cans produced a sample mean of 12.09 ounces, and the Nagel manager knows that the population standard deviation is 0.2 ounce. Thus, the 95% confidence interval estimate for the population mean is computed using this formula, which gives us a result of 12.051 ounces to 12.129 ounces. Based on this sample information, the Nagel manager believes that the true mean fill for all cans is within the following interval. And because this interval does not contain the target mean of 12 ounces, the manager should conclude that the filling equipment is out of adjustment and is putting in too much soda on average. In the Nagel beverage example, the resulting confidence interval estimate for the population mean was at 12.09 plus minus 0.04. The quantity 0.04 on the right side of the plus minus sign is called the margin of error. The margin of error defines the relationship between the sample mean and the population mean. The impact of different confidence level. Now suppose the manager at Nagel is willing to settle for 80% confidence. The corresponding Z value is 1.28 for 80%. Thus, the 80% confidence interval estimate is computed, which resulted to 12.06 ounces to 12.12 ounces. When compared side by side, it can be observed that by lowering the confidence level, the margin of error has been reduced from 0.04 to 0.03. Likewise, when the confidence level is increased, the margin of error will also increase. Another scenario: what if we use a different sample size? Suppose the Nagel Beverage Company production manager decided to increase the sample to 200 cans, which is a four-fold increase over the original sample size. Notice that with the same 95% level of confidence, and by increasing the sample size to 400 cans, the margin of error is reduced from the original 0.04 ounces to 0.02 ounces. With this, the production manager was able to reduce the margin of error without reducing the confidence level. However, the downside is that sampling 400 cans instead of 100 cans will cost more money and take more time. And that's the trade-off. Now let's try a practice drill. A sample of 11 circuits from a large normal population has a mean resistance of 2.2 ohms. We know from past testing that the population standard deviation is 0.35 ohms. We need to determine the 95% confidence interval estimate for the true mean resistance of the population of resistors. You can pause the video for a moment and try to answer the drill by yourself. Now for the answer. By substituting and computing the values in the formula, we are 95% confident that the true mean resistance is between 1.9932 and 2.4068 ohms. Going back to the Nagel Beverage Company application, the manager was dealing with a filling machine that had a known standard deviation in fill volume. You may encounter situations in which the standard deviation for the population is known. However, in most cases, if you do not know the population mean, you also will not know the population standard deviation. When this occurs, you need to make a minor but important modification to the confidence interval estimation process. Now, if the population standard deviation is unknown, we can substitute the sample standard deviation instead. But this introduces an extra uncertainty, since the sample standard deviation is variable from sample to sample. So we use the t distribution instead of the normal distribution. Our standard error now becomes the sample standard deviation divided by the square root of the sample size. And the critical value can be derived from the t distribution table in the following slides. The table here shows the values of the t distribution where the critical values can be found for some selected probabilities. You can again pause the video and take a screenshot of the table for the next 4 slides. DF stands for the degree of freedom and is equal to n minus 1. It is also worth noticing that the t distribution values when the degree of freedom is infinite, or when the sample size is very large, is very familiar. It is because the t values are going towards the z values, or vice versa, as the sample size increases. With the 80% confidence level, it is the same with the t values for infinite degree of freedom. The same with the 95% and the 99%. So accordingly, here is the final formula for estimating the confidence interval for the population mean when the population standard deviation is unknown. Similar with the previous formula, this formula assumes that the population is normally distributed, and if not, a large sample size should be used. Let us look at an example. Heritage Software. Heritage Software, a maker of educational and business software, operates a service center in Tulsa, Oklahoma, where employees respond to customer calls about questions and problems with the company's software packages. Recently, a team of Heritage employees was asked to study the average length of time service representatives spend with customers. The team decided that a simple random sample of 25 calls would be collected and the population mean call time would be estimated based on the sample data. Not only did the team not know the average length of time, but it also didn't know the standard deviation of the length of the service time. If the managers need a single valued estimate of the population mean, they would use the point estimate minutes. However, they should realize that this point estimate is subject to sampling error. To take the sampling error into account, the managers can construct a confidence interval estimate. The first step is to specify the desired confidence level. For example, suppose the Heritage team specifies a 95% confidence level. We need to get the critical t value with 95% confidence level from the t distribution table that was presented earlier with 24 degrees of freedom, which is equivalent to 2.0639. The Heritage team can now compute the confidence interval estimate using equation 8.5 as follows. Therefore, based on the random sample of 25 calls and with 95% confidence interval, the Heritage software team has estimated the true average time per call to be 5.173 minutes to 9.003 minutes.